As you know, in last class we discussed regarding the region of separation, that is the surroundings, on which the antenna influence is felt. If you remember, we discussed antenna as a device and also antenna as a free space. So, when the antenna impedance matches to the free space impedance, antenna releases the signal to the free space. Now, these signals is distributed in this free space, and we say that is the region or the surroundings that receives the signals from the antenna. And this region or the surroundings are broadly classified into two categories: near field region and the far field regions. Now, the signals which is getting released from the antenna is getting distributed in these regions, and these distributions of the electromagnetic fields or the field intensities are function of either the spatial angles like theta and phi in spherical coordinate system, or is function of theta, phi and the radial distance, depending on what region we are handling. For example, if we are talking about the far field region, then this distribution will be the function of theta and phi, that is the spatial angle. But if we are interested in seeing the distribution of this field in the near field region, that the surrounding which is nearer to the antenna, then we see that this distribution is a function of theta phi. In addition to this, it is also function of the radial distance, which is r. So, the distribution of the signals which is getting released from the antenna now can be plotted as function of electric field intensity or magnetic field intensity, that is field intensity. With respect to your theta and phi, or for near field it is theta phi r. It also can be plotted in terms of the power with respect to theta phi or theta phi r in case of near field. So, the graph that is obtained after plotting this field intensity or the power with variation of theta or phi is basically called the radiation pattern of the antenna. So, if I am interested in seeing how the field intensity is getting distributed with the different angles, let us say the situation is like that. I am interested to see how the field intensity is varying with theta. So, in a three-dimensional figure or in three-dimensional space, I fixed my location in terms of the radial distance and in terms of the angle phi. Then I am trying to find out how this electric field intensity is changing with different theta value. Then we see that as we are drawing, maybe our field distribution will take a shape like this. So, here this is nothing but the gain. We will not tell the word gain now because it will be confusing at this moment. We will tell this is field intensity, electric field intensity, which is V per volt per meter, V by M. So, as we are drawing the graphs with variation of theta, putting this as 0, let us say it is 10 degree, it is 20 degree, 30 degree, so like that we are drawing, then the shape which we are now getting, this is called the radiation pattern. Since we are expressing this in terms of volt per meter, that is, we are quantifying this in terms of the electric field, therefore it is called field patterns. Now, instead of this, if I am taking the watt or the power, then in that situation what will happen? Again this theta variation will come, and I will be interested in seeing the variation how the power is changing. That means I will either mention this as watt or milliwatt depending on the measuring device. So, if I am quantifying this graph in terms of the power and the angle, then this particular radiation pattern is called the power pattern. So, if you see here, the radiation pattern basically which is nothing but how this signal which is getting released from the antenna is getting distributed in the surroundings or the regions which is having the influence or the effect of the antenna is nothing but the graphical distribution of the radiated field or the power as the case may be with respect to the spatial angle, specifically when we talk about the far field region, the region which is far up from the antenna. So, radiation pattern basically gives the pictorial or graphical distribution of the field which is associated with the power with the different 3-dimensional angles, how it is distributed in theta plane, how it is distributed in the phi plane. So, based on this distribution, the shape is seen. Based on the quantifying factor, whether it is field or it is power, we classify radiation patterns to 2 categories. One is called the field pattern, another is called the power pattern. If our measuring device is a field strength meter, then obviously this reading will be getting in terms of volt per meter or volt per millimeter. So, obviously the graph which will be getting is nothing but angle versus the field intensity. This will be your field pattern. But if my measuring device is a power meter, if I am measuring the power using a power meter, so obviously the graph which will be drawn with respect to theta will be either milliwatt or watt. So, the shape which will be obtained after this graphical distribution will be called the power pattern. So, that is the way we have 2 type of radiation patterns, either field patterns or the power pattern. Now, as you see from this diagram, this distribution is not uniform. Somewhere it is more, somewhere it is less. Maybe you can come across a situation like this. So, depending on this type of distributions, how the signal is getting distributed in the surrounding regions, we use the terminology in radiation pattern as major lobe, side lobe, back lobe and vestigial lobe. So, let us have a look to the graphical picture which is in front of us. To see this in a animation way, let us have a look to the animation. Now, if you see from this animation, the signal is getting distributed in the space. It is having its angular distribution in a fixed radial distance, out of which one of the direction is having maximum signal. So, the direction which is having the maximum signal, that is called the main lobe. So, like in this blackboard, this is called the main lobe, because out of this distribution, this is the direction in which the signal is maximum. So, it is called main lobe or main beam. This is also called or main beam. Then see, interestingly, this signal again is coming down, meeting a 0 region, almost all null region. Then there is a extension or distribution of the signal in other direction, but it is not having that type of strong distribution, a small lobe distribution like this. The main signal is coming, meeting a null point here, the value is 0. So, this is called null. So, after touching a null, again there is a distribution, the signal is getting distributed over a region in a particular direction, and this distribution is having a field strength or a power which is not equal to the main lobe, but it is less than main lobe. So, this lobe is called your side lobe or side beam, because it appears on the side of the main lobe. So, you will see that side lobes appears only after touching a null. When a main lobe touches a null, then it gets extended, then only the side lobe concept is coming. But mark the picture which is here. Mark the radiation pattern which is drawn in this place or is being shown in the slide here. If you see, this is a main lobe, the signal is getting reduced. Again, before touching a null, the signal has again increased like this. There is a decrease in the main lobe, but again before touching a null, there is a lobe appearing on the side of the main lobe, which is part of the main lobe. This particular lobe which appears on the side of the main lobe as part of the main lobe without touching a null is called vestigial lobe or the vestigial beam. Similarly, the lobe which is exactly in the opposite of the main lobe, like it is shown in the slide, is also called back lobe. So, depending on the distribution, depending on the signal strength, we classify the radiation pattern into main lobe, side lobe, back lobe and vestigial lobe. Now, I will raise a question for you. Let us say we have an antenna which is radiating uniformly in all direction. Like when we are drawing the radiation pattern, imagine that this antenna is radiating like this uniformly in all direction. So, this is a situation, there is no side lobe. This is a situation which is something like called omnidirectional radiation pattern. In a particular plane, it is radiating uniformly in all direction. I'll give you a classification of the antenna based on the radiation parameters, based on the shape of the radiation parameters. As you know, in last class we discussed isotropic, the isotropic radiator. Isotropic radiator or isotropic pattern. When we talk about the isotropic radiation pattern or the isotropic radiator, then we look for those type of radiators which gives uniform radiation in all the planes. For example, if it is a rectangular Cartesian coordinate system which consider, then we will have xy plane, we will have yz plane, we will have xz plane. So, if I take a radiation pattern in xy plane, it should be uniform. If I take radiation pattern in yz plane, again it should be uniform distribution. If I take a radiation pattern in the xg plane, it should be also a uniform distribution. If all the three planes are giving uniform radiations, then it is called isotropic radiator. Can you think of a practical antenna which can give this type of radiation? No. Because any of the practical antenna will go with certain amount of finite conductivity. So, it will lead to certain amount of directionality. That means, they will drive or radiate the signal in a particular direction slightly more than the other direction. So, therefore, isotropic radiator is a very hypothetical terminology, theoretically possible. A point source gives isotropic radiation, but which is not possible in a practical antennas. The antennas which are used, which are fabricated, which are designed by you for practical use, cannot give you a isotropic radiation. But if you are looking for a omnidirectional radiation, yes, it is possible through a practical antenna. Now, let us take the antenna, dipole antenna. In dipole antenna, we have two rods. And is connected to the source. Now, in this situation, if you are seeing the radiation pattern in the cross-sectional region of the dipole antenna, which we name it as, let us say, x and y plane, that means this is a rod. If you are observing your radiation pattern like this and seeing how the distribution is giving a graphical shape, then you will see that it is circular or radiating uniformly in all direction in that particular plane. But if you are going to the x z plane, because if I say this as z, then if you are talking about this plane, x z plane or y z plane, then you will see that means you are seeing from this side. Your rod is in front of you, the dipole antenna is in front of you, and your viewing angle is this. Then in this case, you will find that the radiation pattern is a figure of 8. So, this is a situation where one of the plane is giving you uniform radiation, whereas the other two planes are giving the radiation pattern which is in the shape of a figure of 8. That means, it is having maximum minimum direction including the null points. So, this type of situation is called omnidirectional radiation. That means, it is having in one of the plane uniform radiations, in other plane it is not so. So, basically the study of the radiation patterns are nothing but the study of three components: how the theta components are distributed in far field region, how the phi components are distributed in the far field region, and how these phases are distributed, how these phases are linked with this radiated field. So, based on this, if we are seeing the radiation pattern in the terms of the theta components, then we say it is E theta or S theta distribution, or the E theta patterns or S theta pattern. If this is not in terms of theta, but in terms of phi, then we say it is E phi plane pattern or H phi plane patterns. Now, let us go to very interesting antenna parameters which is attached with radiation patterns. The next important terms or the interesting parameters which is attached with the radiation pattern is called radiation power density. It is called radiation power density. Now, by this time you are aware that this signal gets released from the antenna, get distributed in the surroundings, and these distributions are in different shapes. Depending on these shapes, we name them in different names, and these shapes are nothing but the radiation patterns. Now, when the electromagnetic signal is getting released to the surroundings, basically the electric and magnetic field is traveling down. Associated with this electric and magnetic field is your power and energy. Now, if we take the instantaneous Poynting vector, like the case which I have shown here in this equation, then if E is the instantaneous electric field, H is the instantaneous magnetic field, then the instantaneous Poynting vector is expressed as E cross H. But as you know, this is nothing but a power density. The instantaneous Poynting vector gives a power density. So, if this power density is integrated over the surface, closed surface, that is encompassing this power density, then we get the total instantaneous power. So, that is the reason the instantaneous Poynting vector is integrated over the closed surface, and that is giving you the total instantaneous power. Now, for a time varying situation like antenna, where the electric and magnetic fields are going through a time varying situation, then we are more interested in the average power density, subsequently average power. So, the average power density is nothing but we obtained that by integrating instantaneous Poynting vector over one period and dividing by the period. So, if you see this expression here, this P average is nothing but half RE E cross S star. Now, prior to this, I would like to explain one thing here. When you are talking about the instantaneous Poynting vector, integrating that through a closed surface, you are getting the instantaneous power, total power. Then you are going for a time varying field. Time varying field, you are more interested in the average power. So, this average power in this first expression, you see that I put a 1 by 2, because here this field are peak values. If you are not considering the peak values, then this half will not be there. If you are considering the RMS values, then this P average expression will be RE E cross H conjugate. Now, this total power, so this average power density is this. So, the total power obviously has to be integrated over the surface. So, when we are integrating over the surface, that we get the total radiated power. So, in an antenna system, when especially you are handling the far field radiation pattern, you are not very much interested in the instantaneous power. You are more interested in the average power density, and from this average power density, how to calculate the total power, that is the total radiated power. So, when you have a P average or the average power in front of you, average power density in front of you, integrate that over the surface, then you will get the total radiated power. Now, once you get this total radiated power which is coming out of the antenna and is getting distributed in the surroundings, then this distribution averaged over the distance, like